Okay, so definitely unmute yourself and feel free to ask questions anytime. And also, if you want to type a question or comment into the Discord chat anytime. So last time we were talking about pericyclic reactions. We said there are 3 types of those, and today we're going to focus on 2 of them. The first one was called a cycloaddition. The most common version of a cycloaddition is called a Diels-Alder reaction. A Diels-Alder reaction specifically is a 4+2 cycloaddition. And what's nice about this is it builds up the complexity of the structure. It actually forms 2 new carbon-carbon bonds between this atom here. This is going to be a new bond forming, this bond here, as well as another carbon-carbon bond here. It makes rings or cyclic structures that sometimes are otherwise difficult to make. So it's really a nice addition to any organic chemist's repertoire of reactions to synthesize desired chemical structures. So it's called a 4+2 because there are 4 atoms involved in the one pi system and 2 atoms involved in the other. Now there could be other carbons here. There could be a isopropyl group or a methyl, or there could be X groups here. There could be an oxygen attached, bonded to something, or a carbonyl or a CN group or something like that bonded here. So those substituents could be really anything, which increases the complexity of the structure and gives us more variety and freedom and control over the structure that we're making. But the pi bonds, or the pi system, the system of orbitals that are creating the molecular orbitals that's going to overlap with the molecular orbital from this system, there are 4 atoms with p orbitals overlapping here and 2 here. That's why we get a 4+2. We're going to see a 2+2 as a contrast to that a little bit later. Well, 4+2 is definitely the most common for a couple reasons. One, because it ends up forming 6-membered rings, which have very little ring strain and are relatively stable, which means they're common and they're a feature that organic chemists often need to make in the structures they're trying to form. And the second reason why a 4+2 cycloaddition or Diels-Alder reaction is so common is because the way the orbitals shake out, a 4+2 is a good number to allow for the correct orbital overlap to form these sigma bonds. And we're going to see a contrast with that, between that and the 2+2, where the orbital overlap is not effective and light is needed to make that reaction work. So as we were saying last time, like any pericyclic reaction, the mechanism is concerted, which means it's one step. A one-step reaction requires all the electrons to move at the same time. And we said the pericyclic reactions involve electrons moving in a circle. So I could show this one coming out here to form the sigma bond. This would shift over here to form the new pi bond. This one would shift up there to form a sigma bond. Or we could go the other direction. I could move this up here to form the sigma bond. This could come down here and make the pi bond. And this could come over here to make this sigma bond. So the way you show the arrows moving either counterclockwise or clockwise in a circle doesn't matter. What matters is that it's a circular pattern. You can't move some of the electrons without moving all of them. Like if I just move these to try to form the sigma bond without moving these 2 yet, it might look okay to you because these electrons would swing out there to form that new bond. The other 2 pi bonds haven't moved, so they would still be in their original positions. If we number these carbons, forming a bond between carbon 1 and carbon 6 using those pi electrons. The problem with that is that carbon 6 has a hydrogen and something else already bonded to it. So that would make 5 bonds on that carbon, right? So again, if you're drawing mechanisms, predicting products, trying to understand how the electrons move, it can be really helpful and is critical to think about where the hydrogens are bonded. Because if there's a hydrogen there and I don't realize that, I wouldn't realize how impossible this is to do. I can't make the new sigma bond and create a 5-bonded carbon unless the other electrons shift at the same time. In addition to that, if these pi electrons move out here to make a sigma bond, this carbon only has 1 hydrogen. So it would produce a relatively unstable carbocation. It's stabilized by resonance, and so that wouldn't necessarily be impossible like the 5-bonded carbon is. But the pericyclic reactions involve all the electrons moving at once to avoid impossible or especially unstable intermediates, allowing the reaction to occur. I may ask you to draw a transition state for one of these reactions. So again, in the transition state, we show all the bonds breaking or forming with a dotted line. So we would maybe you want to number the carbons. You might want to draw in the hydrogens to make sure you're not doing anything that would be extremely unstable. But the 4 carbons of one molecule and the 2 carbons of the other molecule, what would happen is any bond that's breaking, which includes all 3 of these pi bonds, because they're all shifting and moving to form a different bond, would be represented with a dotted line. And any bond forming would also be represented with the dotted line. So when these pi electrons move here to form one there, I've got a dotted line there. When these electrons form the sigma bond there, and these form the sigma bond there, I've formed some dotted lines there. So what you end up with is a full circle of bonds breaking, forming all the way around the circle. And that's true for any pericyclic reaction. There shouldn't be any gaps. The breaking and forming of bonds happens circularly all the way around to make sure that none of the carbons end up with 5 bonds. They all have to shift at the same time to avoid any electrons moving to one atom before the other electrons that atom already has moves away from the atom. Notice that each carbon, we'll take a look at this one here. So that one had a couple hydrogens. If I have a carbon with 3 bonds, and if a bond were breaking and the electrons are being pulled away, that would create a partial positive. If more electrons were brought in, it might create a partial negative. But if electrons are leaving as new ones come in at the same time, then there's no partial charge there, because as the old bond breaks and the electrons leave, the new bond forms, and that basically replaces those electrons with new electrons. So there's no partial charge because there's no atom that's temporarily forming a positive or negative. So there's no partial charges we have to show during the transition state. So typically in these reactions, if we want to look at the thermodynamics to make sure that it's going to be product favored, we would focus on the free energy. Most of the time, under most conditions, the products have a lower free energy than the reactants. And so we want to understand the thermodynamics and be able to recognize when that occurs. Sometimes the free energy of the reactants will be lower than the free energy of the products. And so we want to understand what's going to affect the free energy so we can make sure our reaction is product favored as predicted, and that we're not running reactant-favored reaction, expecting to make lots of products. So if we want to look at the free energy change or comparison between the reactants and the products to determine whether the free energy is going up or whether the free energy is going down, which is the case most of the time, we want to look at the free energy formula and the enthalpy term and the entropy term, right? So we're going to do an analysis of that, make sure we can explain the free energy change that's occurring here. So as we're saying, most of these are thermodynamically favored, meaning they're spontaneous or product favored or a negative delta G at low and moderate temperatures. So the Diels-Alder reaction will be product favored, usually at relatively low temperatures. If you increase the temperature, it will shift back toward the reactant side. Okay, so that's the key here. If you have a product favored process, because it's got a negative delta G at a low temperature, but you change the temperature and now suddenly you have a positive value for delta G, that would make the reaction shift back and be reactant favored at the higher temperature. So to understand how temperature affects this process, we need to focus on the entropy and what's happening with this formula when the temperature is changed during the process. So since the temperature is intimately related to the entropy term, it's part of the entropy term, we want to think about the entropy change that's occurring here. Right? So when we think about entropy, the main thing we think about are the moles of reactants versus moles of products. How much variety will exist in the system? Well, if there's two separate molecules that can fly around independently, that's going to be creating more variety than if they're stuck together as one thing. Right? So anytime you go from more moles to fewer moles, you could say the entropy of the reactants is greater than the products. And so we could say the delta S term should be negative, right? The entropy is going down. If we looked at the final entropy minus the initial entropy, there'd be more entropy in the beginning, more variety, because the particles have more freedom to move around in a variety of ways, be positioned in space in a variety of ways. So it'd be subtracting a large number from a small number. And that's why we get, that's why we get a negative value for delta G. So we can't change that, or for delta S, sorry. We can't change that fact that delta S is going to be negative. And so the entropy term has a negative sign in it, and a negative times a negative is positive. So that's why if I increase the temperature, and I increase the size of this positive term, when I'm adding to delta H, it's only going to make delta G more positive, which is going to shift it back toward the reactant side, making it more reactant favored. So let's take a look at delta H. To determine delta H or enthalpy, we look at stability. And the main difference that's occurring here, there is some ring strain, but the six-membered ring has very low ring strain, so that doesn't really factor in. It doesn't really make it very unstable. The main thing that's affecting the stability here are the fact that we have more pi bonds, and then on the product side, two of those pi bonds are converted into sigma bonds, right? So we recall in a pi bond, the electrons are in overlapping p orbitals, and they're above and below the plane of the carbons. They can still attract to both carbons, so still relatively stable, but compared to a sigma bond, where the electron density is mostly in the area of overlap, head-on orbital overlap puts the electron density right between the nuclei. That's a lot more stable. So converting some pi bonds into sigma bonds means that the potential energy or stability is going to start at a high potential energy and go to a low potential energy. delta H is going to be negative. It becomes more stable, lower in potential energy, lower in enthalpy, and so delta H is negative. The enthalpy is going down. So ultimately in this reaction, we have a negative sign for delta H and a positive sign for delta S. And the sign for delta G is going to depend on which of those values is larger. If the negative value is larger than the positive, when I add them, I'll get a negative delta G. That's what happens most of the time. Because the difference between 2 pi bonds and 2 sigma bonds is pretty significant. This is a pretty large negative term. Most of the time, the T delta S term is not going to be big enough to cancel that out and make delta G positive overall. But if you increase the temperature enough, and that increases the magnitude of this value more and more and more, eventually you reach a point where the positive value becomes larger than the negative, and the sign for delta G switches to positive, which means it's going to be reactant favored. So that's why we see the process shifting back toward the reactant side at high temperature versus being more product favored usually at low temperature. Right? And we said the reason that delta S is going to be negative, the delta S is negative, the T delta S term is going to be positive. And so if we increase the temperature, that makes delta G more likely to be positive and shifts it back toward the reactant side, making it more non-spontaneous, is because of the entropy difference. Right? We've got 2 moles of reactants, 1 mole of product. So combining that together decreases the entropy. Also, forming a ring limits the rotational freedom, right? This molecule can only rotate so much. And so that decreases the entropy as well a little bit. And that decrease in entropy is what causes the delta S to be negative and the negative T delta S term to be positive, which is what makes delta G positive when that term becomes larger and larger at higher and higher temperatures. So that's why we can make this conclusion that given the signs for delta H being negative and the T delta S term being positive, as the magnitude of this term increases at higher temperature, is going to cause delta G to become more positive, and that means it's going to be more reactant favored at higher temperatures. So if we want it to be product favored, we want the temperature to be as low as possible. If we decrease the temperature more and more and more and get it as low as possible, this term, even though it will remain positive, will start to decrease. It will start to approach 0, and it won't be very significant, in which case the negative delta H term will make delta G more and more negative, or more and more product favored. So the lower the temperature, the more product favored it will be. Is there a disadvantage to lowering it too much? Yeah, there's a kinetic disadvantage, right? Because we still have to get enough energy to make it over the transition state. So the lower the temperature, the more of a free energy difference there is between the reactants and the products. I get a more and more negative delta G value. And that favors the products more when it reaches equilibrium. But if I lower the temperature too much, then the collisions that occur between these reactants won't have enough energy to get to the transition state. So even though the product is favored, it won't form often enough to build up in solution in a reasonable time frame. So this is a situation where there's a balance between thermodynamics and kinetics. Anytime thermodynamics favors the products at lower temperature, it's going to be in conflict with kinetics, which will favors higher temperatures to make the process reach equilibrium sooner. So that's why typically, if you're going to run a reaction like a Diels-Alder reaction, you would try to find a research article that describes the temperature they used, the solvent they used, the length of time they allowed the reaction to go for, so that if they're getting a good yield of the product, you can use the same conditions they did, and they probably took the time to optimize the temperature so that it was low enough that the products were as product favored as possible, but high enough that the process was happening in a reasonable time frame and was kinetically feasible. So those are the general thermodynamics of a Diels-Alder or 4+2 cycloaddition. We want to talk a little bit more about this reaction in detail. So a lot of times people use the term Diene and dienophile. So I know the dienophile especially can be confusing to students. Really all that is an alkene. Right? The Diene, the di means two, the ene means alkene. So here we have two alkenes that are conjugated. Right? So the diene is always going to be conjugated. It has to be conjugated because in order for this reaction to work and the circle of electrons to move without breaking any noble gas configurations, all the carbons involved with breaking and forming bonds have to be sp2 hybridized. So it has to be fully conjugated. There has to be p orbitals on every atom here, overlapping all the way around the top and the bottom, as well as here. We're going to see in a little while how the orbitals play into the process. But the one with two alkenes and four p orbitals is called the diene, because there's two alkenes. And the other one is really just an alkene, but we call it dienophile because it likes or can react readily with dienes. So one is a diene, and the other one is the one that wants to react with the diene, or the dienophile. If you look experimentally at the simplest molecules that could potentially undergo a Diels-Alder through this mechanism, and you look at the product that would be produced, you would see that the activation energy necessary is so high and the temperature needed to facilitate the collisions is so great that when it reaches equilibrium, it ends up being reactant favored. Right? We said we need a low temperature to make a product favored thermodynamically. So if we want this reaction to be successful, there are some limitations. There has to be some way of lowering the activation energy so we don't need such a high temperature to facilitate the collisions necessary to make the product. We need to be able to keep the temperature relatively low so that when it reaches equilibrium, it'll still have a negative delta G rather than the positive delta G we see at the much, much higher temperatures. All right, so at the high temperatures, the thermodynamics favor the reactants, and we can't get a very good yield of the products when it reaches equilibrium. If I didn't increase the temperature for this particular reaction, though, these reactants won't produce a product kinetically because it requires too strong of collisions. So we want to look at the orbitals that are involved and think about how can we facilitate these collisions and allow the process to occur at a lower temperature without requiring this amount of energy to reach the transition states. And so that usually requires what's called an electron withdrawing group on the dienophile, or the alkene, or the part of the reaction that has the two carbons with a pi system. And if you look experimentally at an alkene that has an electron withdrawing group, you get much higher yields at room temperature. You don't need a high temperature to reach the transition state. So somehow this group is facilitating this reaction kinetically. And we know the product's already favored at low temperatures. The problem is normally we can't get the product to form quickly at low temperatures, but somehow this is speeding the process up. So it doesn't have to be an aldehyde, it could be a ketone or an ester, a carboxylic acid, or a cyano group. Any one of these groups is an electron withdrawing group because each one of these groups, through both induction and resonance, pulls electrons out of the dienophile or out of this alkene. Right? So let's look at how that happens. So we'll just use this one as an example. So we know that through induction, the oxygen's more electronegative than carbon, so it pulls these electrons away and creates a partial positive. Also through resonance, the pi electrons could shift up there. So there's a minor but significant resonance contributor that would look like this. And that increases the quantity of positive that sits on that carbon and allows the pi electrons here to shift up through another resonance contributor, also minor but significant. Which would distribute that positive onto another carbon. So this carbon here is also carrying a fair amount of partial positive due to the resonance shifting of the electrons up to the oxygen. So that means this alkene is electron deficient. And that makes it a little unstable. That increases its energy. So if it starts at a higher energy, it doesn't require such strong collisions to get to the transition state. And you can also think of it, since it's now positive, because the electrons have been pulled away, both through induction, because of the partial positive here, pulls this away and creates a little partial positive here, and through resonance, shifting the electrons up, creating a partial positive here. That positive starts to attract the electrons from the Diene and gets the electrons flowing around in a circle. And so that attraction also helps to facilitate the collisions and the electron movement, and makes the process occur without as much energy needed for the collisions. We're going to look more at the stereochemical outcome in a little while, so actually I'm going to skip this slide here. We're just showing you the variety of the Diels-Alder reaction and what you can do with it. Just, I guess, to point that out, if you want to create a ring where the substituents are positioned on the same side, you'd want to make sure that they start on the same side of the alkene. Because if they're trans and they start on opposite sides, they'll end up trans on opposite sides, right? There's no time for this alkene to rotate. The electrons will swing out, and all these electrons move at once. All the new bonds form at once. So when these new sigma bonds form, there's no time for this bond to rotate. And if the X group start on opposite sides, they'll end up on opposite sides. You can also do a Diels-Alder with a dienephile that is an alkyne. We still have the electron withdrawing groups, creating some nice partial positives here. That facilitates the reaction, speeds it up. And those partial positives pull electrons away, making some partial positives here through induction as well as through resonance. When these electrons swing out, these could swing over here and create a positive here. When these swing out, these could swing over here and create a positive here. So there's a lot of partial positive here, and that helps to attract the Diene to the dienephile. So if I'm doing this reaction, and I've got a triple bond with some things bonded here, maybe this particular example, it's the same reaction. One pair of electrons swings out to form a sigma bond, so does another, and then this pair swings in to form this alkene. So this alkene is formed here when this electron pair swings up here. As the other electron pairs swing, they make the two sigma bonds. So these are the new bonds that are forming as the old bonds, the old pi bonds here shift. But only one of the pi bonds from the triple bonds move, so the other pi bond is still there. And so if you want to make a six-membered ring, a Diels-Alder is a great way to do that. If you want the six-membered ring to have one alkene, then during the mechanism, this electron pair shifting here would create that. If you wanted to have a second one, you want to start with an alkyne so that when one pi electron pair shifts over, there's still another one there left behind to form that double bond. All right, so let's just see if we can predict some products here, and then we'll talk about the stereochemistry and the orbitals a little bit later. All right, so here I've got a Diene, a got an alkene, a dienophile that's got electron withdrawing group pulling electrons away, and that's going to attract these electrons and create some partial positives here. So that's going to help draw in this pair of electrons. It's going to form a sigma bond between this carbon, so let's number these. So I want to focus here in a Diels-Alder reaction specifically on the carbons that are going to be breaking and forming bonds. So carbon 1 is going to form a bond to carbon 5, the way I happen to have them numbered. As carbon 1 forms a bond to carbon 5, this pi bond will come out here and form a bond between 6 and 4. And then this pi bond can come over here. So I can have the electrons flow around clockwise, or I could have shown them flowing the other direction. Either way, it doesn't matter. What's going to happen now is a 6-membered ring involving those 6 carbons. So 5 and 1 connected, and 4 and 6 connected, and this pi bond is going to be here between 2 and 3. This pi bond is gone. It's now a sigma bond between 6 and 4. This pi bond is gone. It's now a sigma bond between 1 and 5. But then I have to put the other substituents in properly. So there's still a methyl group here on carbon 2. That doesn't go anywhere. There's still a methyl group on carbon 1. But now this is a chiral center. So I have to decide, is this methyl group here on carbon 1 going to be pointing out at me or pointing away? Well, that's going to depend on the spatial positioning of the groups when they collide and form the new sigma bond. So what's going to happen here is the collision here is not going to be like a head-on collision. Right? So what we have to think about is the Diene has these p orbitals, and the dienophile also has p orbitals. And the p orbitals of one have to sit down on top of the p orbitals of the other. And so it's more like a sandwich. One of these pi systems is kind of a flat structure with the p orbital sticking up and down on it, and the other one's going to come down and sit on top of it. The p orbitals have to start overlapping head on instead of side by side in order to make the new sigma bonds. So if the alkene comes in from the top, it would push this methyl group down. If it comes in from the bottom, it would push the methyl group up. So the methyl group here could have either of the two spatial positionings on that new chiral center. Carbon 6 has 2 methyl groups. So whichever one of them would be pointing down, one of them would be pointing up. I don't know which. And carbon 5 has this group here. And so again, depending on whether the alkene approaches the diene from the top or from the bottom, that would potentially create a situation where that group has sometimes a solid wedge and sometimes a dashed wedge. Here I have a Diels-Alder product, right? I already see the 6-membered ring form. So this would have been formed through a Diels-Alder reaction. But we know, since it doesn't have much entropy, if we increase the temperature, it will react to give a greater entropy. And that will go through the same mechanism, but instead of the electrons swinging around in a circle to form new sigma bonds, I would just show them swinging around in a circle to break the sigma bonds. So I have these swinging around. This sigma bond is going to break and end up as a pi bond. So let's number these carbons. So carbon 1 and 2 already have a pi bond. This sigma bond is going to come over and form a third bond there. So between 1 and 2, I end up with a triple bond. It's carbon 1 and carbon 2. When these electrons swing over here, they're going to make a pi bond between 3 and 4. So there will be a new pi bond here. These electrons, this pi bond is going to swing up here, so now it'll be between 5 and 6. 5 still has a CN group. 3 has 2 methyl groups. So that's one way to think about the retro Diels-Alder reaction. And that's a reasonable answer for that question. However, there's another possibility. When I see an electron withdrawing group, a CN group looks like this. And the nitrogen, through resonance, can attract electrons, the pi electrons, and create a positive here. And also through induction, attracting, because it's more electronegative, and create a positive here. So this group is going to attract electrons away from this carbon. And an electron withdrawing group, we said, in a Diels-Alder usually is placed on the dienephile, not the diene. So the way we just did that and the way we moved the electrons created this side of the ring as the diene, and these two were the dienephile. Probably makes more sense to do it the other way though. And so if I move this sigma bond here, that will make the triple bond. That will have probably been my dienephile. These would move here, and these would move here. So if I draw the product of that, I get a triple bond between, I'll number them differently. I don't remember how I numbered them a minute ago. I would get a triple bond between 1 and 2, and carbon 1 would have the CN group as an electron withdrawing group. That helps to make the dienephile more reactive toward the diene. So then between 5 and 6, I'd form a pi bond. Between 4 and 3, I'd form a pi bond. And then 3 would have a couple methyl groups attached to it. So if I wanted to make this, I would start with these two reactants, and since I have a CN group here, that makes the dienephile more reactive because it's an electron withdrawing group, more likely to attract the electrons in and produce the Diels-Alder product. I'd have to increase the temperature quite high to shift that back toward the reactant side, where the entropy favors that side because I have 2 moles instead of 1, right? So anytime you have different amounts of entropy that you can see on both sides, a higher temperature should shift the reaction toward the side with more entropy. All right, so let's take a look at the orbital overlap that needs to occur to try to understand this reaction in a little bit more detail. So what has to happen, as we said, is the dienephile, which is going to be an alkene, is going to have some p orbitals. And then the diene is going to have some p orbitals. And the alkene is going to have to sit its p orbitals down right on top of the dienephile's p orbitals. They have to come in and overlap head on, right? So this thing's going to come up here and sit down so that the bottom of this orbital can overlap with the top of this one head on, and the bottom of this one can overlap with the top of that one head on to make the 2 new sigma bonds. That requires the diene to take on an S-cis conformation. Right? We said last time the single bond can rotate. If it rotates and the alkene flips up here, it's more stable because the hydrogens avoid some steric repulsion. If the single bond then rotates again and the alkene flips back down into the S-cis form, then these hydrogens with their orbitals kind of getting close together and repelling, it makes it less stable. So only like 2% of the molecules will exist in this form. Almost all the molecules exist in this more stable form. But if I look at the S-trans version of the alkene and the p orbitals that are there, the 2 p orbitals on the ends, those are the ones that have to overlap with the alkene or the dienephile to form the 2 new sigma bonds. Here, they're too far away. There's no way for the alkene to overlap its orbitals with both of those because they're too far away. So a Diels-Alder reaction cannot happen when the diene is in the S-trans form. It does not allow for the proper orbitals to overlap head-on to form the new sigma bonds in the Diels-Alder reaction. And so the Diels-Alder reaction can only proceed when the diene adopts an S-cis conformation. And since most of the molecules don't exist in the S-cis conformation because of the steric hindrance between the hydrogens, this is a real limitation for this reaction. It would be a slow reaction because a molecule, 98% of the molecules would look like this. Once in a while, a rotation would occur and it would look like this, but then it would have to collide with the alkene and do the orbital overlap to make the Diels-Alder reaction before it rotates back to the S-trans. And that would only happen once in a while. And so the whole process is going to be prohibitively slow. It's not going to work very well. Just to answer this question, we said, well, the more stable one is the S-trans because of sterics, the sterics between the hydrogen. So we got a problem here. We can't just do a Diels-Alder on any diene, because if the diene exists mostly in the S-trans form, it's not reactive in that form. And this slide here proves that, right? I can make this alkene or by it, this diene. This diene is rotationally prohibited from forming the S-cis, right? This bond cannot rotate because the ring is holding things in place. So there's no way to get that alkene on the same side of the single bond as the other alkene and form an S-cis. So this one, the p orbitals that would have to overlap head-on with this alkene, if one comes over here and they line up and they overlap head-on, the other one is too far away. It would have to stretch too far to overlap. So the reaction cannot occur, right? So we can confirm this orbital overlap that's necessary to make the Diels-Alder reaction by showing that when we don't allow the orbital overlap because the two carbons that are involved in that are too far apart, it doesn't give any reaction. So if the diene can rotate from the S-cis into the S-trans, and almost all the molecules look like this, it's not going to be very reactive. If the diene is stuck in the S-trans, it's not going to be reactive at all. However, if the diene is locked into the S-cis conformation, then it should be much more reactive. So in the S-cis conformation, we said the two alkenes have to be on the same side of the single bond that's connecting them. So how do we lock that into place? Well, we could form a ring. So putting the two alkenes in the ring and then locking that with an atom or with two atoms should lock that into place so that the orbitals then are the right distance apart for the alkene's orbitals to come down and overlap head-on to make the new sigma bonds. So that means that S-cis, locked in S-cis dienes should be pretty reactive toward a Diels-Alder. In fact, the cyclopentadiene, which is this one here, is so reactive, it will react with another cyclopentadiene. Right, so one of the molecules will act as a diene, and the other will act as a dienophile. So let's say this is the dienophile. One of the pi bonds here is going to overlap with just put that other carbon up there so it's out of the way. Here are my other two pi bonds. So these two molecules are the same. I just took this extra carbon here and bent it up so it'd be out of the way. So I've got these p orbitals here. So this one is going to overlap here, and this one is going to overlap here, and they're going to overlap head-on to form a new sigma bond. Right, so if I'm looking at the mechanism, I would expect this pair of electrons to come out here. These would move over here, and then this pair would come down here. So it's same Diels-Alder mechanism, same reaction. Oops, I lost my other double bond. That double bond's not moving. So this double bond comes out to form a sigma bond. And so does the other one. Maybe I should count these carbons up. 2, 3, 4, 5. 6, 7, 8, 9, 10. So the pi bond between 2 and 3 is still there. 5 is going to connect to 9. And 1 is going to connect to 6. Actually, I didn't really do that very well. Let's fix this. 1 is actually more likely to connect to 9 back here. This electron pair would move in here, and then this electron pair from 6 would come out to 5. The way I angled things, 6 would probably come down and overlap on top of 5, the way I showed it here. And 9 would come down and overlap on top of 1. So 5 would be connected to 6, and 1 would be connected to 9. 6 and 9 are bridged with carbon 10. And there's also 7 and 8. Which would have a pi bond between them because one of those pi bonds shifts over there. So this would be dicyclopentadiene. Right? This is cyclopentadiene. And this is cyclopentadiene. And when the two of them react together through the Diels-Alder reaction, you have two cyclopentadienes connected. So you have a dicyclopentadiene. And the reason that that goes forward, as we were saying before, is because two pi bonds get converted into two new sigma bonds. So when the molecule is restricted to the S-cis conformation, which this is because of the 5-membered ring, it's very difficult to prevent it from reacting. It usually just reacts because of the sigma bonds being more stable than the initial pi bonds. And so we can do a similar reaction here. We've got the same thing. We've got a diene. Here we've got a nice dienophile because these CHO groups look like this. CHO, they're electron withdrawing. They create a lot of partial positive here, and that helps to draw in the electrons from the alkene. So when you have this ring, what you probably want to think about doing is to get the CH2 that's not really part of the pi system and isn't involved in the mechanism, just kind of out of the way. So if I'm numbering these just to show how that would look, 1, 2, 3, 4, 5, this would be 1, 2, 3, 4, and 5. And there'd be alkenes here. So I could show the electrons shifting around counterclockwise or clockwise. I think I've been showing them going counterclockwise a lot. So I'll move these ones clockwise. So this electron pair can move here. This electron pair would move out here to form a sigma bond, and then this would move here to form that sigma bond. So the product I would get these 5 carbons. Carbon 2 would now be connected to what was, we'll just call this 6 and 7, which would, carbon 2 would be connected to 6. 6 would be connected to 7, and 7 is making a bond to 5. This moves over here and becomes an alkene between 3 and 4. And then these two aldehyde groups are still on 6 and 7. So that brings us to a stereochemical question. As we were saying, just redraw this real quickly. The p orbitals here have to overlap with the p orbitals of the alkene. As that overlaps, and those orbitals start to form sigma bonds, there's no time for this bond here to rotate. So if this alkene can never rotate, the two aldehyde groups are always going to be on the same side. They're either going to be both positioned here, or they'd be both positioned here. So they're kind of down positions and up at an angle position, similar to a chair, right? When you have a chair, oops, draw it very well. When you have a chair, there are axial positions and there are equatorial positions. So this isn't a chair, so it's not the same thing, but there are positions that come straight down in this bicyclic system. Those are called endo, and then the positions that are coming up and out at an angle, those are called exo. So if the two groups on the alkene or the dienophile are on the same side, like cis, then they're going to end up both endo or both exo. It's impossible to form the alternative where one group would be down in an endo position and the other would be out in an exo position. It's also impossible to form the other alternative where one is endo and the other is exo. To make those, I would have had to start with a different alkene. I would have had to start with the aldehyde groups in a trans position. Then they would end up in opposite spatial positioning with respect to one another instead of the same positioning with respect to one another, which is what you get when they're on the same side of the alkene. So be careful with the stereochemistry. All right, we just talked about that. And so these are the two products you could make from that reaction. If you do this reaction experimentally, the reaction we just talked about using cyclopentadiene and this molecule, this alkene or this dienophile with these two electron withdrawing groups, since they're on the same side of the alkene, that means it's cis, or in this case also Z, because the two parity groups are on the same side of the alkene. If you start with them there, as we said, they have to end up on the same side, either both endo or both exo. And if you do the experiment and measure the amounts of those that are formed, you find this one happens to be the major product. And so there's an explanation for that, which we're going to talk about in a minute as well. There's actually a little bit more sterics down here than there is up here. It's similar to axial versus equatorial. In the axial position, the ones that are pointing straight up or straight down, there's other groups, right? These two are kind of like eclipsing one another, and they're kind of crowded. The equatorial groups point out kind of away from the structure, and so there's a little bit less crowding. So these two are still kind of eclipsing one another, which isn't as stable, but it's still pointing away from the rest of the structure for the most part. So while the exo may be thermodynamically favored, because it's a little less steric hindrance, it's not the major product. And so if it's thermodynamically favored, but it's not the major product, it must be kinetically disfavored, or the other one must be kinetically favored. So there must be something happening during the transition state that makes this one form more often than the other one if it's the major product, despite having a little bit more steric hindrance and not being quite as stable as the other product. So here's what's happening. London forces. So what's happening here is the p orbital here and here are overlapping with these, right? That's what forms the new sigma bond, the head-on orbital overlap between these p orbitals. As they start to overlap their lobes with the same wave sign and constructively interfere to form a sigma bond, they, at that moment, rehybridize into sp3 hybridized carbons, here, 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 and here. And that, again, you know, that sigma bond forms from the head-on orbital overlap of the sp3 hybridized orbitals. And so these p orbitals rehybridize to sp3 and orbital overlap head-on to form the new sigma bond. Meanwhile, there are other p orbitals over here and p orbitals on this aldehyde group. And those pi clouds there can shift around, and the pi clouds here can shift around, and that allows some London forces to form, right? We know if I have two structures and they're going to attract, if they're nonpolar, which these are relatively nonpolar, or at least one is not, the hydrocarbon here is nonpolar, for them to attract through London forces, the electrons have to shift a lot to one side versus the other. So the more loosely held the electrons are, the more readily they can form partial charges to attract. And pi electrons are pretty loosely held, right? Because when two carbons form a pi bond, the pi electrons are above and below the plane. So the disadvantage is they're not that close to the nucleus and they're not stabilized by the attraction of the nucleus that well. But the advantage for forming intermolecular attractions is because they're not that tightly held, they can shift around and create, maybe shift to one side temporarily for a moment and create some partial charges. So if this pi cloud gets close to this pi cloud, but their electrons can shift around a little bit, it can allow one to shift away and create a partial positive and the other to shift toward that and create a partial negative. So there's attractions. Get rid of some of the scribbles. There's some attractions between the pi electrons there and the pi electrons here. And that's why it's more stable during the transition state for those groups with pi electrons to end up in endo positions. Because during the formation of the bond, they end up kind of tucked underneath here. Despite the sterics, they end up tucked underneath there specifically so that their pi cloud and this pi cloud can shift around a little bit and create some London force attractions. And that's also called pi stacking. That's why sheets of graphite or sheets of graphene in graphite will stack on top of one another because their pi electrons can shift around and form London forces. So pi stacking also occurs in DNA. When DNA forms a double helix, the DNA base pairs pi stack on top of one another. It's been shown that you can take out naturally occurring base pairs and replace them with ones that have more pi bonds, and it actually makes the DNA double helix stronger because of the extra pi stacking. So pi stacking stabilizes this molecule during the transition state, and the pi interaction there of those clouds forming some London force attractions makes it more stable to occur with those tucked underneath ending up in the endo position versus if they were pointing out here away from the structure in the exo position, they wouldn't be able to form those attractions underneath the structure. So is this a kinetic or thermodynamic argument? It's a kinetic argument. If we were to look at the energy diagram, and we can imagine these two reacting in two different ways, with these tucked underneath, or it could flip over. So let me just draw that as best I can. So we're going to still do the same thing here. But we're going to flip this alkene over like a pancake, so the aldehyde groups are now facing the outside. and they'll end up in exo positions. So when that happens, they're too far away from any of this other electron clouds to form any London forces. So during the collision, them pointing away means it's not as stable. So let's call this one the exo transition state. We'll call this one the endo, where the groups end up tucked under in the endo position in the end. So we expect overall, since we're forming sigma bonds from pi bonds, that the final energy be lower than the initial energy. We also expect the exo product where the CHO groups are pointing away to be a little bit more stable in the end because of sterics. But the endo product is the major product because it forms through a lower energy pathway. During the transition state, the pi-pi interactions here form some attractions during the transition state. And the exo that doesn't have that goes through a higher energy transition state despite being more stable in the end. So we're already planning to keep the temperature relatively low, right? We said earlier, if we increase the temperature, then delta G won't be negative anymore. If we increase the temperature too much, then it will be the opposite. It will be reactant favored for the free energy change. So we have to keep the temperature low, and that actually favors the kinetically favored product, because with the low temperature, it'll have enough energy to go through the lower energy transition state once in a while, but very rarely will it ever go through the higher energy transition state to produce the other product. So despite the exo product being thermodynamically favored, it's not kinetically favored, and so it's not the major product of the reaction. So as long as the groups on your alkene have pi bonds, which they usually do because those make the best electron withdrawing groups, and we need the electron withdrawing groups for the reasons we're about to talk about to make the process work kinetically, they usually will primarily end up in the endo position. But again, they have to be on the same side of the alkene if we're going to be on the same side here, both down or both up. And so just to point out one more time, if you do this reaction with the trans version of the alkene, you cannot get this where they're both in endo positions, because if they start on opposite positions, only one of them can be endo, the other would have to be exo, or vice versa. All right, so let's see if now we can understand this a little bit more detail, looking at the orbitals, and also be able to explain why the 2+2 cycloaddition is not effective using heat like the 4+2 cycloaddition is. So we're still looking at the 4+2. We've got butadiene, which looks like this. And once in a while, this will rotate into the S-cis, which is what we need to react with ethylene or ethene. So one reason this reaction won't work well is because most of the molecules will exist in a form where the orbital overlap isn't possible, which we already talked about. Even though here, even with this, if we could somehow get the molecule into this S-cis form and think about the electrons moving around, we could try to make this product, but the transition state energy is still relatively high without electron withdrawing groups on the alkene. And so we want to try to understand that a little bit by looking at the orbitals. So what's going to happen here, as we've been saying, is the alkene, or I'm sorry, the diene is going to have a pi system, and the alkene is going to have a pi system, and the p orbitals have to overlap in order for this to work. So which orbitals are overlapping? Because in this system here, there are 4 molecular orbitals. 2 bonding molecular orbitals that have electrons and 2 anti-bonding orbitals that are empty. And if we look at the alkene, there are 2 orbitals. There's a pi bond and a pi antibond that's empty. So would it be favorable for the HOMO of one to overlap with the HOMO of the other? Would it be favorable to have an orbital that's full of electrons overlapping with another orbital full of electrons? No, that would just create more repulsion between the electrons. So that's not going to work. When Diels-Alder and other pericyclic reactions occur, we want a full orbital to overlap with an empty orbital. That way, when the overlap occurs, there's only 2 electrons and they can both go into the bonding molecular orbital that results from that overlap. We don't want 4 electrons because then 2 would have to go into the anti-bonding orbital and that would be much less stable. So what we're talking about here is the HOMO of one compound, because it has 2 electrons, and the LUMO of the other because it's empty, those are the orbitals that have to overlap. Those are the orbitals that will allow 2 electrons to then get into the bonding molecular orbital that creates as a result, that's created as a result of that orbital overlap. And so we can think of the dienophile attracting electrons from the highest energy occupied molecular orbital of the diene into the lowest energy unoccupied molecular orbital of the dienophile. It's not a transfer, it's going to be an overlap and those electrons are going to be shared, but that's really what we're thinking about. If that occurs and the LUMO is much higher in energy than this HOMO, it's not going to be favorable. Why would the electrons want to go into a much higher energy orbital? That's not going to be a process that's favorable, and it's not going to happen often because it's going to require a lot of activation energy to push those electrons out from their nucleus into a higher energy orbital. So what we need to do is entice those electrons into this orbital, and that's why we add the electron withdrawing groups. The electron withdrawing groups also will help to create a partial positive, and that will help to attract the electrons in there and stabilize them as they're moving in there, lowering the transition state and making the process happen more often. Right? So that's one important aspect of the orbital overlap. Another important aspect of the orbital overlap is called orbital symmetry. So when we're thinking about taking a pi system, if we're converting pi bonds into sigma bonds, what that's going to involve is a p orbital and another p orbital, and they're going to approach one another head on. But if they're going to form a bond, a bonding molecular orbital, they need to do so in a way where the signs of the 2 orbitals overlapping head on have the same sign to allow for constructive interference rather than destructive interference. So in the textbook, they use these pink and blue colored lobes to represent the different wave signs. We could imagine the pink is the negative wave sign and the blue is the positive wave sign. Any p orbital has 2 lobes with opposite wave signs. So how do I know where the positives are and where the negatives are? Well, we have to go back and look at what we just said. We have to look at the HOMO of the diene overlapping with the LUMO of the dienophile, right? So we're getting the wave signs from these pictures. The lowest energy one has all constructive interference, and those electrons are very stable, so that orbital is not involved in any kind of rearrangement or movement for the electrons. It's the HOMO that's occupied that has one node. It's a little bit less stable. Those are the electrons that are higher in energy. They're going to be the ones that start to move into the new molecular orbital created by overlapping with this one. Right? So we're not overlapping the 2 HOMOs. We're overlapping the HOMO of one with the LUMO of the other. And what that means is we need to line up the outside p orbitals with these p orbitals so that the signs will match. So the positive side of one can overlap with the positive of the other and do constructive interference to make a new sigma bond. And the negative of this can overlap with the negative here and do the same thing, right? So that's what we're talking about over here. The LUMO has one node. Here the HOMO has one node. And that just happens to work out nicely because this carbon here has a positive wave sign and this carbon here has a positive wave sign. And so they can come in and start to overlap and do constructive interference. And it's just also nicely set up for the negative of this to overlap with the negative of this and also do constructive interference to form the new sigma bonds. If either one of these involved destructive interference because it was a positive and a negative overlapping, it wouldn't work. You can't form a sigma bond without constructive interference. And also note, as the orbitals overlap, the hybridization of these 4 carbons changes from sp2 to sp3. So this is sp3. The sp2 has p orbitals. Once the p orbitals start to overlap, it rehybridizes to sp3 to get better overlap and allow the carbons to get the optimal distance and make nice stable sigma bonds. So let's take a look at the 2+2 cycloaddition and explain why that doesn't work nicely like the 4+2 does. The 4+2 is the one we just saw right there. 4 p orbitals in this molecule and 2 in the other, so it's 4+2. In the 2+2, if we look at the orbitals that are involved, both the molecules look like this, right? They would both only have one pi bond. So if we replicate this, I'll just do it over here. So if we look at one alkene, there's one molecular orbital that has constructive interference and no nodes. And then there's a higher energy molecular orbital that's not occupied. So this would be the HOMO. This would be the LUMO. That has destructive interference. So that would be for one alkene. And the other alkene would have to have the same thing. Constructive interference in the HOMO and destructive interference in the orbital that's not occupied, the lowest energy unoccupied molecular orbital. So to make this work, the two HOMOs can't overlap because they're both full of electrons. That would just cause repulsion. So the HOMO of one would have to overlap with the LUMO of the other. But hopefully you can start to see that's not going to work. So we can draw the mechanism, which I forgot to do. Let's just do that real quick. The mechanism would involve this pair of electrons swinging out to form a sigma bond here, and this pair swinging out to form a sigma bond there. So I'd still convert 2 pi bonds into 2 new sigma bonds. So I'm forming some ring strain. That makes it a little unstable. But the sigma bond's still more stable than the pi bond. So this reaction could, you can still imagine it working at least to create an equilibrium where some of the molecules would exist with the sigma bonds rather than the pi bonds. But we don't see any of it forming. And the reason for that is because it's not so-called symmetry allowed. If the HOMO of one has to overlap with the LUMO of the other, we can't get constructive interference when we overlap both carbons, right? This carbon here, it can overlap with this one. That will create constructive interference. But then when this one overlaps here, a positive and negative, that's going to create destructive interference. Both new sigma bonds can form, but only if there's constructive interference. So this is not going to work. This would create a node where the negative wave sign and the positive wave sign overlap rather than a bond. And so I can't form this because the symmetry of the orbitals does not allow for constructive interference in both areas of orbital overlap. And so that's what we're seeing here. So if the HOMO and LUMO, the HOMO of one allows electrons to move into the LUMO of the other to form the new sigma bond, the positives could line up if both of these were positive, right? Because they have to come in at the same time and both line up. But if one positive lines up with the negative, it's not going to give you the constructive interference you need to make a new sigma bond. And we can't have, so when one LUMO overlaps with the other HOMO, which is what we're seeing here, we can't form sigma bonds at both positions because we don't get the right orbital overlap. You could imagine the HOMO of both of them overlapping. That would work. One would just have to flip over so that the negatives line up with the negatives, or the positives come over here and line with the that would form sigma bonds. But if they're both full of electrons, there's too many electrons. And so that's not stable. We only need 2 electrons in our areas of orbital overlap so that they can be stabilized. So that means that because the orbital overlap is not effective to create constructive interference, we can't make that product effectively through a Diels-Alder reaction. It's called symmetry forbidden. The orbitals don't have the right wave sign to overlap to create the sigma bonds properly. However, this reaction can be done. What's required is light. It won't work when it's thermally initiated. Right? Using heat is not going to make it easier for these orbitals to overlap. The fact that they have the opposite wave sign is precluding them from doing effective overlap. And increasing the temperature is not going to change that. But using light will, if it's the right wavelength and it has enough energy to overcome the energy difference between the HOMO and the LUMO, it can excite an electron in one of the molecules up to the next energy level. And now that this is occupied, it becomes the highest energy occupied molecular orbital. So now we have a situation where the excited molecule, its HOMO, can interact with the LUMO of the other molecule. And now it is symmetry allowed, right? Because this LUMO right here, if we redrew it, there's a positive, not negative, negative, positive. So just to maintain the orbital wave signs for that LUMO. If we overlap that with now the HOMO of the excited ethene molecule, it could flip over and we'd have a positive, negative, negative, positive. This, if we flip the structure over, this negative would be here, and the positive would be here. So now it is symmetry allowed. Both areas of overlap allow for constructive interference. And so this reaction can work under the right conditions. If we use light to excite one of the molecules up, it's what was its LUMO will become its HOMO, and that can overlap with the LUMO of the other, and that will allow the orbitals to properly overlap as we just showed. So you can make cyclobutane from molecules of ethene if you excite them with light first or in the process. Questions about that? All right, so that leads to the first quiz question, which is a retro Diels-Alder. So in a retro Diels-Alder, you are breaking apart a ring to reform the initial Diels-Alder reactant. So to do that, one thing you want to look for is an electron withdrawing group. If there's an electron withdrawing group here, creating a partial positive. Probably these two atoms that are right next to that started as the Diene file. And so I want to push some electrons there and break these away over here and move these up here. Right? The circle of electrons is the Diels-Alder reaction. The mechanism for the forward Diels-Alder is really the same as the retro Diels-Alder. It just involves moving the electrons around in a circle. Every time a pair of electrons moves one spot over, the other electrons have to move one spot over to avoid a 5-bonded carbon, and then the other electrons move one spot over to replace electrons on the carbon that they were initially taken away from. So that's going to break this sigma bond and this one. If we were doing the Diels-Alder, we would have formed those, but now we're breaking them. So this piece is now on its own. It has oxygen here. These pi electrons are now here. And this sigma bond is now here. And that can also just be drawn this way. Those are meant to be the same thing. When these sigma bonds shift over here, the other product of that retro Diels-Alder reaction has a 5-membered ring. And those electrons would swing in there and make the other pi bond, which would be connected to the ester group. So if you're not seeing that, hopefully if I number the carbons, that might help. So I'll just number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 7, 8, 9, and 10 are these ones. And 1, 2, 3, 4, 5, 6 are these ones, right? So the sigma bond ends up as a pi bond between 2 and 6. This sigma bond ends up as a pi bond between 9 and 10. And this pi bond that was between 8 and 9 shifts over to be between 7 and 8. All right, so that's our Diels-Alder discussion. Fairly detailed discussion. There's a lot of detail there for you to practice in some examples from the textbook. And we're doing, or at least attempting to do, a Diels-Alder reaction in Lab 3. And if you're not getting success with that this week, you might want to think about modifications you can make that might make the reaction more effective, and we could potentially look to see what we have on the shelf as alternative reactants to hopefully at least allow you to do some kind of Diels-Alder reaction for Lab 3. But at least in lecture, we need to move on here to the second type of pericyclic reaction known as electrocyclic reactions. In the electrocyclic reactions, we said one sigma bond is formed and one pi bond breaks. So that's the main difference between electrocyclic reactions and Diels-Alder reactions. In the Diels-Alder reaction, we had 2 sigma bonds forming from 2 pi bonds breaking. Here it's only 1. Right? So the mechanism is basically the same. We can use this to form 6-membered rings or 4-membered rings. And what's going to happen is we initially have 3 pi bonds, now we have 2. Here we initially have 2, now we have 1. So we're converting one of those pi bonds into a sigma bond in both cases. The difference between these two, and the reason why one favors the products and one favors the reactants, is because of the ring strain, right? So in the 6-membered ring, there's very little ring strain. When the electrons shift around, this pi bond and this one end up still remaining pi bonds. So there's really no reason why they would necessarily care one way or the other. But this pi bond shifting out here to form a sigma bond, that is the main driving force for this reaction. So there's a decrease in entropy because you're forming a ring which restricts rotation. But there's also a decrease in enthalpy because you're going from a pi to sigma. And in that case, usually that's a larger value, right? When I'm looking at delta G, if the delta S term is negative, I have a negative times a negative, this whole thing becomes positive. So again, I'd have to keep the temperature kind of low. I can't keep it too low or it won't work kinetically, but I want to keep it relatively low so that the negative delta H still makes delta G negative and it will still remain product favored. With the four-membered ring, though, I'm still going to have a negative delta S because I'm still forming a ring that restricts the rotational variety or freedom. But in this case, forming the pi bond into the sigma bond is kind of offset by the formation of the ring strain, the angle strain of the electron pairs getting too close on the same atom, the torsional strain of the hydrogens eclipsing and repelling their bonds. So that ring strain means that delta H might not be negative, or if it is, it might be a very small negative. And in which case, the positive, the T delta S term, would outweigh that and make delta G positive, which would cause the process to be more reactant favored. So these reactions are potentially possible, but they're not really that product favored because of the ring strain when you go for the four-membered ring. But the six-membered ring can happen, and there are lots of examples of that you can look at. So let's take a look at the outcomes of these electrocyclic reactions in a little bit more detail, especially from a stereochemical perspective. So here I've got a reactant. It's got a triene, 3 alkenes, and I can imagine this reaction or the mechanism where 2 of the electron pairs shift around to form new pi bonds, and the other one comes out here to form a new sigma bond, closing the ring. The methyl groups here have a very specific spatial positioning, right? They're both pointing out. Here, one is pointing in and the other is pointing out. And so what we see is, depending on the conditions used to initiate the process, whether it's light or heat, I get different reaction, right? So if I start with this reactant and I use light, I get a trans positioning of the methyl groups. If I use heat, I get a cis positioning of the methyl groups. They're on the same side of the ring. If I start with this reactant, depending on whether I use heat or light, I get different outcomes. So we want to be able to explain that stereochemical outcome for these reactions, and in order to do so, we've got to look at orbital symmetry. So just like we were looking at the orbitals properly overlapping to form the constructive interference to make the sigma bonds here, we want to look at the same thing in the context of these reactions. So if I have a triene, I've got to look at what the orbitals, what the p orbitals look like, what their wave signs are, so that we can form this new sigma bond through constructive interference rather than destructive interference. All right, so here we go. We've got an alkene. So let's say I've got this structure here. There are p orbitals on each carbon. There's one molecular orbital where there's all constructive interference on the top and all constructive interference on the bottom. That one really stabilizes the electrons, so it's not going to be the one that's involved. We want to focus on the HOMO, the highest energy one, right? Those are going to be the electrons that benefit most from switching from a pi bond to a sigma bond. And so it's the highest energy electrons that we want to focus on, right? So how do we know what the orbital's wave sign should be? Well, in the lowest energy one, as we said, 6 carbons, 6 p orbitals, there'd be full constructive interference all the way around the top. and full constructive interference all the way around the bottom. In the next highest energy one, there'd be a node. And the nodes always start in the middle and kind of work their way out every molecular orbital that you go up in energy. So with only one node, it would be right in the center, and there'd be constructive interference over here, and constructive interference over here, but destructive interference where the node is. So there'd be 2 electrons here, 2 electrons here, but I've got 2, 4, 6. I've got 6 total pi electrons. So these orbitals are holding 4 of them, and they only have one node. They're not very unstable. So the next highest would be holding 2 electrons. That's going to be the HOMO, the highest energy one that's actually occupied, because it's holding the other 2 of the 6 pi electrons. And if the last one had 1 node, this one has 2 nodes. If we look at where those nodes are and the wave signs that produce those nodes, you see there's some areas where there's some destructive interference. But the key here is to focus on the wave signs for the outside carbons here. Because what's going to happen is, when we look at the wave signs, if this is plus minus here on that end, and then we look at the other end, and this is also plus minus, in order to make the new sigma bond, this will have to rotate in so that the 2 wave signs match and do constructive interference to make the new sigma bond, right? So if this is plus plus and minus minus, and that's the way it should be, because this is the orbital we're dealing with, and we have pluses on the same side on the outside and negatives on the same side on the outside. There's 2 ways to form the sigma bond. These 2 areas with the same wave sign can rotate in, or these 2 areas with the same sign can rotate in. The terminal carbons rotate to form a sigma bond. As they rotate, they rehybridize from sp2 to sp3, so you can get good head-on orbital overlap between the positives once they are overlapping. And as this rotates, it's going to change the spatial positioning of these methyl groups. Right? So if there's a methyl group here pointing out and one here pointing out, I find it especially useful to make a model and then rotate the model, imagining that these p orbitals initially are perpendicular to the flat plane of the molecule. Those p orbitals that are perpendicular have to rotate in so that they're facing one another, overlapping head-on. And then if you make a model, all you have to do is look at where the methyl groups end up in that rotation. Right, so this is what we're talking about. One way to imagine it is the negative areas rotating in and overlapping head-on. If these methyl groups are still in the plane initially, pointing out here, what's going to happen as this rotates up is it's going to pull them down, and they're going to end up pointing down. Right, so they'd be both ending up with dashed wedges because of the way the p orbitals have to rotate in order to overlap with constructive interference. That just pulls the methyl groups down due to that rotation. You could also imagine the same type of rotation, but maybe the positive wave signs overlap to form constructive interference. So if that rotates down in and that rotates down in, and we're just using a loop to show the rest of the molecules so that we don't have to draw as much complicated stuff, then I would get orbital overlap between 2 positive wave signs, which would also be great. If this rotates down in, that's going to rotate those methyl groups up into solid wedge positions. So because of the way the orbital signs work out, and the fact that they have to overlap head-on with the same wave sign one way or the other, that means that the methyl groups, because of their initial spatial positioning, have to be both down or both up. If you can't see that, I highly recommend you make a model of the structure Imagine where the p orbitals are. Rotate the carbon so the p orbitals face one another through constructive interference, and you should see the methyl groups rotating either both up here or both down. You wouldn't form the product with one methyl group with a solid wedge and the other with a dash wedge, because that would only result from the destructive interference. The words disrotatory and conrotatory, I think, are generally confusing. I don't really focus on them too much, but disrotatory specifically means that the two orbitals rotate in opposite directions. So one is rotating clockwise and the other is rotating counterclockwise. That's what disrotatory means. The type of rotation that will occur will be whatever rotation is necessary for the orbitals with the same wave sign to overlap. So that's really should be your key focus. I wouldn't worry too much about whether the rotation is conrotatory or disrotatory. Focus on making the rotation allow for the p orbitals to rotate in and head-on overlap with the same wave sign so that they can give you constructive interference. So here we have a slightly different example. We have the possibility of making a four-membered ring, right? So these electrons could swing here, these could move out here. If only those two pairs of pi electrons move, this one moves here and forms another pi bond. This one moves out between these two carbons to form that sigma bond. So what type of rotation is it going to be? Oh, in order to understand why we get different stereochemical outcomes depending on where the methyl groups are located, we have to understand what the wave signs of these p orbitals are, so we know what way they have to rotate and where the methyl groups will end up after that rotation. So if we're dealing with 4 carbons, we want to try to focus on what the orbitals will look like. So the lowest energy orbital would have full constructive interference on the top and the bottom. That one would not be the key one to focus on. That one would hold 2 electrons. It's not the highest energy occupied molecular orbital. The highest energy occupied one would be the next one up, where there'd be one node in the middle. It would also be holding 2 electrons, the highest energy electrons of the pi system. So there'd be constructive interference on one side of the node and constructive interference on the other side, but destructive interference across the node. So here I'm looking at one orbital on the outside having that distribution of the wave signs, and the other orbital on the outside having the opposite distribution of the wave signs, negative on top, positive on the bottom. So in this case, in order to get the areas to overlap with the same wave sign, if I'm imagining these orbitals here in this case, the methyl groups are kind of both pointing out. One orbital has positive on the bottom, the other has positive on the top. So here I'd have to rotate, if I want to get the negatives to overlap, I'd have to rotate it like this. If this rotates up, this methyl group will end up with a dashed wedge. If this rotates down, the methyl group will follow it because it's connected, and it'll rotate up into a position with a solid wedge. Right, so I can figure out the stereochemical outcome by looking at the HOMO, imagining the rotation of the orbital so that the same wave sign overlaps. That's the key there. We could do the same thing down here, and we would see a different stereochemical outcome because of the positioning of the methyl groups. This particular example is conrotatory because both rotations are counterclockwise, 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 or I could focus on the positive wave sign, that happening clockwise, and so is that one, right? So in order for the same wave time to overlap, I get conrotatory either way. And because of the way the methyls were positioned in space, they're going to follow that rotation and end up with solid wedges or dashed wedges accordingly. So this is really much more helpful if you look at some models. And when we're in lab, feel free to bring this up with me and we can look at the models on some of these examples. All right, so we want to look at this quick example here. To do an electrocyclic reaction, I would expect the electrons to move around in a circle. And just to draw the product that would produce, Nothing is happening at this carbon, so I would expect that methyl group to still be there with the same spatial positioning. This electron pair has moved out here. This electron pair has moved here. This electron pair is now forming a sigma bond. That'd be this one here. And then I've got these two methyl groups. So if I just draw the methyl groups here without using a solid or dashed wedge, that's not right, because these two centers are both chiral centers. And I have to be specific about whether the methyl group here has these methyl groups that are on these two carbons have solid wedges or dash wedges. Maybe I'll number these just to make sure we're all on the same page. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So the methyl group on 9 and the methyl group on 10 need wedges or dashes. So what I would do is I'd make a model of this. I'd look at how many pi electrons there are. There are 6. So I would draw all the molecular orbitals that are occupied, and I would focus in on the highest energy one that's occupied. And if there are 6 pi electrons, the 2 in the lowest energy one and the 2 in the next lowest energy one, that would account for 4 of them. So there'd be 2 in the third energy orbital, and that would have 2 nodes. So this would be the same type of situation we saw earlier, where the outside carbons would have a positive on top and a negative on the bottom. And so the positives would have to rotate in order to overlap properly. So if you had a model of that, you would hold those p orbitals both pointing in the same direction, and then you'd rotate them in so that they can overlap. And if you do, you'd find that the two methyl groups both have solid wedges, or you could also draw them both with dashed wedges. But you can't draw one solid and one dashed, because that's not something that would form. It wouldn't form in this case because of the orbital overlap that occurs has to have the same wave sign. It's really hard to show without the model. So I definitely encourage you to ask me about that in lab so I can demonstrate with a model. If you use light, you get a different outcome, because light excites an electron up from what was the highest energy occupied molecular orbital to the next one, which was the LUMO. So this was the LUMO. It didn't have any electrons in it. But when I use light, I excite an electron up into that. And that changes things, right? So before the excitation, the outside carbons would have had to rotate disrotatory to get the positive to overlap with positive or negative with negative. Once I excite an electron up to a different orbital that has different nodes, the orbital symmetry is different. So now I would have to do conrotatory rotation in order to get the outside carbons to have the same wave sign overlapping to do constructive interference. So if we look at that example, what would the product be? So let's just say this was the reaction we were doing. We're moving the electrons around in a circle. We're forming a new sigma bond here, but we've got a couple methyl groups. We want to know where in space do those methyl groups end up. Well, this one would have to rotate down as this one rotates up in order to get the same wave signs overlapping. As this one rotates down, the methyl group would follow it and end up in an up position. Oops. So this is going to move here. Actually, let me redraw that. I'll draw it more like I have it here. Try to be consistent. So this is going to rotate here. This pi bond is going to shift over here. This pi bond is going to make the new sigma bond. So there are two methyl groups here, one on this carbon and one on this carbon. As this bond rotates in, that methyl group is going to rotate up. As this rotates in, it's going to pull that methyl group down. So the spatial positioning here has to be trans. Even if I rotate the negative wave signs in to overlap, I would still end up with trans. I would end up with the opposite. This one would be dashed, and this one would be solid. But I don't form the cis. I don't form the molecule with the methyl groups on the same side, specifically because the orbital overlap has to occur with constructive interference. And the orbital I'm dealing with, which used to be the HOMO, but now is, or it used to be the LUMO, but now is the HOMO because I excited an electron into it, that's the orbital that determines the rotation that's required and where the methyl groups will end up as a result of that rotation. All right, so let's take a look at this one. So here I only have 2 pi bonds. So if I'm going to do an electrocyclic reaction, I would shift 1 pi bond in to make a new pi bond, and the other would shift out here to make a new sigma bond. So I then have these 2 alpha groups attached there. So this 5-membered ring serves as an anchor. It's still there. It's got, I always do that. Try to draw it the same way. Okay, it's got this methyl group here. This electron pair is going to swing in here to make a pi bond. This electron pair is going to swing out there to make a sigma bond. So I'll have a 4-membered ring forming there. And I'll have 2 alpha groups on these 2 carbons. But I don't know if they need solid wedges or dashed wedges. So I need to look at the orbitals that are involved. So I'm focusing on those 4 carbons. And I need to know where the wave signs are. So I need to know what orbital I'm dealing with. Normally, if I have 4 pi electrons, I've got 4 p orbitals. With 4 pi electrons, there are 2 occupied orbitals, right? Because I can fit 2 electrons in each orbital. The lowest energy one has all positive on the top, all negative on the bottom. The next one would have 1 node, but since I'm using light, I'm exciting an electron up from there into the next energy level, which would have 2 nodes. So you have to make sure that you recognize which of the molecular orbitals you're dealing with that's going to form the new sigma bond. So here, when I fill in the signs to make the proper nodes, I see that the outside carbons are going to have wave signs that look like this. Those alpha groups are facing in. And so now, at this point, it's especially helpful to have a model because I want to see when the positive rotates down and overlaps with the other positive, what's going to happen to the rotation of those alpha groups. So when this rotates in, that alpha group is going to end up rotating down. And when this rotates in, that's going to rotate that alpha group down as well. Pretty sure. Just double check that with my model real quick here. So I got 4 carbons. I have my p orbitals sticking up out of the plane. I'm going to rotate them in. I've got my ethyl groups sticking in toward one another. And when that occurs, I did it correctly. The ethyl groups would both be pointing down. Alternatively, if the negative part rotated in to overlap between both carbons, those 2 ethyl groups would both be pointing up. So I have one molecule where they both have dashed wedges, and then I'd have a second molecule where they both have solid wedges, but I would not form any of the molecules where one is dashed and one is solid because of the way that the HOMO I'm dealing with has the wave signs aligned. So to correctly predict the stereochemical outcome, you really need to look at the orbitals and the rotation that results. For a ring opening, it would be the same thing. I would do the same mechanism, break open the sigma bond to avoid to open up some of the ring strain, move that pi bond over there. So I can draw the product pretty easily here. The question then is, where are these ethyl groups? Are they pointing up here? Are they pointing down there? Are they positioned spatially so that there's more sterics or less sterics? So your instinct would probably be to put the ethyl groups here to avoid steric repulsion. But I don't know if they'll end up there because I have to look at the molecular orbitals that are involved. So again, if it's 2 pi bonds and light, the molecular orbital I'm dealing with has 2 nodes. And what's going to happen here is these orbitals are initially overlapping with the same wave sign. And when they open, they have to open up like this because this is the orbital that I'm dealing with when an electron is excited. So when these p orbitals that are currently overlapping head on rotate away from one another, they have to rotate so that the positives both end up on top and the negatives both end up on the bottom. And so if one of my ethyl groups has a dashed wedge and one has a solid wedge, I would make my model reflect that. I would rotate the p orbitals so that they're not overlap anymore, and then look at where the ethyl groups end up. And this is not the product I get when I do that. I don't have space to draw it, so I'm going to get rid of that. The product I would get after that opens up would have one of the ethyl groups here and the other here. So despite the steric hindrance between that ethyl group and the hydrogen, and that not being nearly as stable as it would be as the one I drew before where the ethyl groups are pointing away from one another, I can't form the one where the ethyl groups point away because it's not allowed by the orbital symmetry. The orbital symmetry in these pericyclic reactions is critical to being able to predict the correct stereochemical outcome. And so that brings us to the other quiz question from today, where we're doing an electrocyclic reaction, just like the ones we were just talking about. It's a ring opening, and we want to be able to give the product with the proper stereochemical configuration. So to do this, I can think about the mechanism first. I know that these electrons are going to swing around in a circle, because that's how pericyclic reactions work. The sigma bond here is going to open up. So the sigma bond is no longer going to be here. It's going to swing in here and form a pi bond. This pi bond over here is going to swing up here. This pi bond swings out there. I still have a methyl group here. I still have a methyl group here. Those really aren't really relevant because they're on sp2 hybridized carbons. They don't have any chance to be positioned differently spatially. But the methyl group here, here, and this ethyl group have a specific spatial arrangement. And that's going to determine whether they end up pointing up here or away. I should probably draw that a little bigger so things don't get too crowded. Right, so on this carbon, all of this is in the same plane, so the p orbitals can all overlap. There's going to be something here and something here. And on here, there's going to be something here and something here. I don't know whether it's going to be, so there's a hydrogen here. So for this carbon here, I don't know which spot is going to be occupied by the methyl and which is occupied by the hydrogen. And the same thing here. I don't know that unless I look at the orbitals that are involved. So when I have 6 carbons, and I'm focusing on the orbitals, the big question is, what are the wave signs in these orbitals? What orbital am I dealing with? If heat is involved, I'm dealing with whatever the normal highest occupied molecular orbital would have been, whatever the normal HOMO would have been. And when there are 6 electrons, the normal one there is going to have 2 nodes. So I'll have a node here. Oh, that's not right. When I've got 6 of them, 0 nodes is the lowest in energy, 1 node is the second lowest energy. So there'd be 2 nodes, and those 2 nodes would be here and here, not here. Let me just double check that in my mind. Here and here. That's right. It looked weird going around in a circle. So with this molecular orbital with 2 nodes, when I think about the signs that are going to occur there to create the nodes and to create the constructive interference in the area where there is no node, for this to open up, initially these 2 positives on the end carbons are going to be overlapping to make the constructive interference. That is going to have to open up. So really, again, this is much easier to see with a model, and I definitely would be happy to go over this with you in lab with a model. But if you make the model and you have the 6 carbons involved, and you take their p orbitals and overlap them head on to make this initial sigma bond here. You want to then put the methyl and ethyl groups on properly so they're spatially positioned correctly. Right? So I'd make my model here. I would have a sigma bond here. Instead of having a sigma bond, I'd probably just put 2 groups there facing one another to represent the sigma bond. I'd have this methyl group pointing out at me, this one pointing out at me, and then the ethyl group pointing away. So then I have to open this up in such a way that as these overlapping orbitals pop up, they end up producing this arrangement. So I don't want the positives to be on opposite sides. They have to be on the same side. If I were using light, it would be the opposite, because then I would be dealing with the next highest energy orbital, because an electron would be excited up to it. So when I open this to put the 2 positives on the same side, that rotates the methyls in such a way where they end up pointing away from one another. So that produces this product here, where then the ethyl ends up pointing in. That creates a lot of sterics, so it's not really that stable, but that's one of the products I would observe from the orbital analysis. Alternatively, if the orbitals were to open up facing both on the bottom, then the other product I would get would look like this, where the 2 methyl groups would end up facing one another, and the other group would be pointing away. So now I've got these 2 methyl groups facing one another, and that's going to create some steric hindrance. So either way, it's not really stable. Whatever the least steric hindrance one is, where the one with the least steric hindrance would have the ethyl group facing away and this methyl group be facing away, and that hydrogen would be in there because it's smaller. It wouldn't create as much sterics, but I don't get that one. The orbital symmetry doesn't allow it to form. So there's different combinations of positioning for the ethyl and methyl groups, but I only form 2 different possible products because of the orbital symmetry that's involved. So if that's confusing to you spatially, don't feel bad. It's probably confusing to almost everyone. It's definitely confusing to me, and it was especially confusing to me when I first tried to learn this stuff. So working with the model and thinking about the orbitals, there's steps involved with that, and I can definitely help you get through those steps individually if you take the time to discuss it with me in lab, ideally tomorrow, since we're going to have an exam on this next week. If you're one of the people who normally comes in on Tuesday, you're welcome to contact me and schedule something sooner. We could meet on campus potentially, and we could work with the model kits for me to explain that to you. So please let me know. And then Woodward and Hoffman basically put all this stuff together into a series of rules depending on how many pi electrons there are. You could memorize the type of rotation But to me, when I memorize things, my memory often recalls it incorrectly. So I think it's probably a better idea to simply make the model, look at the orbitals, make sure you rotate things in a way that allows the wave signs to properly overlap, and that should allow you to get the correct stereochemical outcome. And the worst case scenario, even if you don't get the right stereochemical outcome, as long as you can show the electrons moving, you'll be able to get credit for drawing the mechanism. And if you draw the product, maybe the correct product, but it doesn't have the correct stereochemical outcome, that also would be worth a lot of partial credit. So do some practice on that. Go over some examples together if you like sometime. And then next week on Monday, we're going to keep drudging forward by finishing the sigmatropic rearrangement section of Chapter 17 and getting into Chapter 18, which is about aromatic rings. We're going to do a couple chapters on aromatic rings. So you want to prepare yourself for that, as well as being able to answer the quiz questions for day 12 on Monday. All right, so that's all I have for that. I have a meeting, as you noticed, popping up on my screen, a notification to enter a meeting at 3, so I'm going to jump off now and go to that meeting. But please feel free to contact me anytime if you do have any kinds of questions.